Space is vast. It's filled with billions of galaxies. The universe harbors enigmatic objects known as black holes. Gravity is so strong that nothing, not even light, can escape. Black holes challenge our understanding of the universe. The concept of black holes might seem like something straight out of science fiction. However, these objects are very real. They play a crucial role in the evolution of galaxies and the universe itself. Understanding black holes allows us to probe the fundamental laws of nature. It's like peering into the engine room of the cosmos. Black holes are not empty voids. They are incredibly dense concentrations of matter packed into an infinitely small point called a singularity. Imagine the entire mass of our sun squeezed into a space the size of a city. That's the level of density we are talking about. The singularity is a place where the known laws of physics break down. This breakdown of our understanding is part of what makes black holes so captivating. They present a profound challenge to our scientific models. Yet, they also offer an incredible opportunity to expand our knowledge of the universe and its workings. Black holes are not static objects. They grow by consuming matter and energy from their surroundings. As they pull in material, they can heat up surrounding gas and dust to incredible temperatures. This process creates some of the brightest and most energetic phenomena in the universe. Despite their destructive potential, black holes are also essential for the evolution of galaxies. They can influence star formation. They can even shape the distribution of matter on the largest scales. They are both creators and destroyers, shaping the cosmic landscape over billions of years. Their existence raises more questions than answers. What happens to the information that falls into a black hole? Is it lost forever, or is it somehow preserved? Could black holes be gateways to other universes or dimensions? These are just some of the mysteries that continue to fascinate scientists and the public alike. Black holes are often misunderstood. People imagine them as cosmic vacuum cleaners, sucking up everything in their path. But this is a misconception. Black holes exert gravity, just like any other object in the universe. The difference is that their gravity is incredibly strong due to their extreme density. Imagine standing on the surface of the Earth. If you throw a ball up, it will eventually fall back down due to the Earth's gravity. Now picture a hypothetical object with much stronger gravity. If you throw the ball up with the same force, it might travel much higher, but it will still fall back down. However, if this object were dense enough, there would be a point where even the fastest ball, even light itself, couldn't escape its gravitational pull. This point of no return, the boundary beyond which nothing can escape, is called the event horizon. It marks the edge of the black hole's influence. Section 2. Event Horizon, Point of No Return. The event horizon is not a physical barrier. It's not a surface you could touch or see. Instead, it's a region of space-time so warped by gravity that all paths lead inwards, towards the singularity at the heart of the black hole. Think of it like a waterfall. Once you're past the edge, there's no going back. The size of the event horizon depends on the mass of the black hole. A black hole with the mass of our sun would have an event horizon with a radius of only a few kilometers. In contrast, supermassive black holes, found at the centers of galaxies, can have event horizons spanning billions of kilometers. As you approach an event horizon, the curvature of space-time becomes increasingly extreme. Time itself slows down relative to observers farther away. This effect, known as time dilation, is a direct consequence of Einstein's theory of general relativity. Section 3. Stellar ghosts, remnants of giants. Black holes come in different sizes. The most common type, stellar mass black holes, form when massive stars die in catastrophic explosions called supernovae. These explosions occur when a star exhausts its nuclear fuel and can no longer support itself against its own gravity. During a supernova, the star's core collapses under its own weight. If the core is massive enough, at least 3 times the mass of our sun, the collapse continues unabated. The core gets squeezed into an infinitely small point, the singularity, and a black hole is born. These stellar remnants are scattered throughout galaxies, often hidden from view. They can be detected by their gravitational influence on nearby objects, such as stars or gas clouds. As they pull in matter, they can create accretion disks, swirling disks of superheated gas that emit powerful X-rays. Section 4. Supermassive giants, lurking in the darkness. While stellar mass black holes are impressive in their own right, they are dwarfed by their much larger cousins, supermassive black holes. These behemoths reside at the centers of most, if not all, large galaxies, including our own Milky Way. They can have masses ranging from millions to billions of times the mass of our Sun. The formation of supermassive black holes remains an active area of research. One possibility is that they formed through the mergers of smaller black holes over billions of years. Another scenario is that they originated from the collapse of massive gas clouds in the early universe. Supermassive black holes play a crucial role in the evolution of galaxies. Their immense gravity influences the orbits of stars and gas clouds, shaping the structure of galactic centers. They also drive powerful jets of energy that can extend for thousands of light years, heating surrounding gas and regulating star formation. Section 5. Miniature Mysteries, Seeds of the Early Universe. In addition to stellar mass and supermassive black holes, there's a hypothetical third category, miniature black holes. These tiny black holes, some potentially smaller than an atom, are thought to have formed in the extremely hot and dense conditions of the early universe, shortly after the Big Bang. Unlike their larger counterparts, miniature black holes are not formed from the collapse of stars. Instead, they are predicted to have emerged from quantum fluctuations in the fabric of space-time itself. These fluctuations, tiny ripples in the otherwise smooth fabric of the universe, could have concentrated enough energy to create these primordial black holes. Miniature black holes remain theoretical. They have never been directly observed, and their existence is still debated among scientists. However, if they do exist, they could provide valuable insights into the nature of gravity, quantum mechanics, and the conditions of the early universe. Section 1. Stellar Nurseries, the birthplaces of stars. To understand the origins of black holes, we must first journey to the stellar nurseries scattered throughout the cosmos. These vast clouds of gas and dust, often spanning light years across, are the birthplaces of stars. Imagine a cosmic ballet where gravity orchestrates the movements of these interstellar particles. Within these clouds, gravity draws together clumps of gas and dust, causing them to collapse under their own weight. As these clumps contract, they heat up, much like a bicycle pump gets warm when you compress the air inside. This heat increases the pressure within the clump, pushing outward against the inward pull of gravity. Initially, the outward pressure from the heat counteracts gravity's relentless pull. However, as the clump continues to contract and heat up, something remarkable happens. The temperature at the core of the clump becomes so intense, reaching millions of degrees Celsius, that nuclear fusion ignites. The life and death of stars. Nuclear fusion powers stars, sustaining them for millions or billions of years. Inside a star's core, hydrogen atoms fuse under immense pressure and heat. This fusion forms helium, releasing tremendous energy. This energy radiates outward, counteracting gravity. A balance between gravity and fusion defines a star's lifespan. The star's fate is sealed by its initial mass. Section 3. Gravitational collapse, the inevitable end. For stars like our Sun, this balancing act eventually ends when they exhaust their nuclear fuel. Without the outward pressure from fusion, gravity takes over. The star's core contracts, heating up even further as it is compressed. This heat causes the star's outer layers to expand, transforming it into a red giant, engulfing any nearby planets in the process. Eventually, the outer layers of the red giant drift away, forming a planetary nebula, a cosmic cloud of glowing gas and dust. The core, now a dense, hot object called a white dwarf, cools slowly over billions of years. White dwarfs are the final remnants of stars like our Sun. Their nuclear fire is extinguished, their fate a gradual fade into darkness. However, for stars much more massive than our Sun, the story takes a more dramatic turn. These stellar giants, after burning through their nuclear fuel at a furious pace, face a more violent and spectacular end, leading to the formation of extreme objects like neutron stars and black holes. Section 4. Neutron stars, extreme matter, and pulsars. As a massive star exhausts its nuclear fuel, its core collapses rapidly under its own immense gravity. This collapse compresses the core, squeezing electrons and protons together to form neutrons. The core becomes a giant nucleus of almost pure neutron matter. This neutron star, only a few kilometers across, spins rapidly. Some neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. These beams sweep across space as the neutron star rotates. Section 5. Black hole formation, crossing the event horizon. For stars exceeding a critical mass, even the immense resistance of neutron matter cannot halt the relentless crush of gravity. The collapsing core continues to contract, becoming denser and denser, its gravity growing stronger and stronger. Eventually, the gravity becomes so intense that nothing, not even light, can escape its grasp. A black hole is born. At the heart of a black hole lies the singularity, a point of infinite density where the known laws of physics break down. Surrounding the singularity is the event horizon, the point of no return. Once something crosses the event horizon, it is forever trapped within the black hole's gravitational grip, destined to be pulled toward the singularity. Black holes are the ultimate cosmic traps, regions of space-time warped by gravity to such an extreme that they challenge our understanding of the universe. Their formation is a testament to the power of gravity, a force that shapes the cosmos on the grandest scales. Section 6. A cosmic balancing act, supernovae, and stellar recycling. The formation of a black hole is often accompanied by a spectacular explosion known as a supernova. This catastrophic event, brighter than billions of stars combined, can outshine an entire galaxy for a brief period. The explosion disperses the star's outer layers into space, enriching the interstellar medium with heavy elements forged in the star's core. These heavy elements, the building blocks of planets and life itself, are scattered throughout the galaxy, seeding the formation of new stars and planetary systems. In this sense, supernovae and the black holes they sometimes leave behind are not just destructive events, but also acts of cosmic creation and renewal. Black holes, despite their enigmatic nature, play a crucial role in the cosmic cycle of stellar evolution. They are both endpoints and beginnings, shaping the universe and influencing the formation of the next generation of stars and galaxies. Understanding black holes is essential for unraveling the grand narrative of the cosmos. Section 1. Beyond the Veil, a journey into the unknown. Imagine venturing beyond the event horizon, crossing the point of no return. What awaits on the other side? Our understanding of physics breaks down as we approach the singularity, the heart of a black hole. It's a realm where gravity reigns supreme, distorting space and time beyond recognition. Current scientific theories struggle to describe what happens inside a black hole. The singularity, a point of infinite density, challenges our fundamental understanding of matter and energy. It's a cosmic enigma, a place where the known laws of physics cease to apply. Despite the challenges, scientists have developed theoretical models to explore the bizarre physics at play inside these cosmic behemoths. These models, based on Einstein's theory of general relativity, offer glimpses into a realm where space and time are intertwined, and gravity's pull is inescapable. Section 2. Spaghettification, the ultimate cosmic stretch. One of the most intriguing and terrifying predictions about black holes is the phenomenon of spaghettification. Imagine falling feet first towards a black hole. As you approach the event horizon, the gravitational pull on your feet becomes significantly stronger than the pull on your head. This difference in gravity, known as a tidal force, stretches your body like spaghetti. The closer you get to the singularity, the more extreme this stretching becomes. Your body would be elongated and compressed along the direction of the black hole's gravity. Eventually, the tidal forces would become so strong that they would rip you apart, atom by atom, a process aptly named spaghettification. While spaghettification is a dramatic and somewhat gruesome concept, it highlights the extreme nature of gravity near a black hole. The tidal forces, a consequence of the difference in gravitational pull across an object, demonstrate the immense power of these cosmic objects. Einstein's theory of general relativity tells us that gravity affects not only space, but also time. The stronger the gravitational pull, the slower time flows. This effect, known as time dilation, becomes increasingly pronounced as you approach a black hole. Imagine two identical clocks, one far away from a black hole and the other falling towards it. As the falling clock approaches the event horizon, it would appear to tick slower and slower from the perspective of the distant clock. At the event horizon, time would appear to stop altogether. This distortion of time is a mind-bending consequence of general relativity. It means that an observer falling into a black hole would experience time differently from an observer watching from a safe distance. Inside the black hole, time itself would become a meaningless concept, another casualty of the singularity's grip on reality. At the heart of a black hole lies the singularity, a point of infinite density where all the matter that falls into the black hole is thought to be concentrated. It's a place where the known laws of physics, as we understand them, break down. Our current theories cannot describe what happens at the singularity. Some physicists speculate that the singularity might not be a point of infinite density at all, but rather a region of extremely high but finite density. Others suggest that quantum effects, which govern the behavior of matter at extremely small scales, might play a role in preventing the singularity from becoming infinitely dense. The singularity remains one of the most enigmatic and challenging concepts in physics. It represents a fundamental limit to our current understanding of the universe. Unraveling the mysteries of the singularity could revolutionize our understanding of gravity, quantum mechanics, and the very nature of reality itself. In the 1970s, Stephen Hawking proposed a revolutionary idea that challenged the traditional view of black holes as inescapable cosmic traps. He suggested that black holes are not entirely black, but emit a faint radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, arises from the creation and annihilation of virtual particle-antiparticle pairs near the event horizon. Occasionally, one particle of the pair falls into the black hole while the other escapes, carrying away a tiny amount of energy from the black hole. Hawking radiation is incredibly faint, far too weak to be detected with current technology. However, its theoretical implications are profound. It suggests that black holes are not eternal but slowly evaporate over time, albeit over incredibly long timescales, far exceeding the current age of the universe. Section 6. Echoes from the Abyss, Probing the Heart of Darkness. While directly observing the interior of a black hole remains impossible, scientists are developing innovative ways to study these enigmatic objects indirectly. One promising avenue is the detection of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. The merger of two black holes, for example, releases an immense amount of energy in the form of gravitational waves. These waves, predicted by Einstein's theory of general relativity, can be detected by sensitive instruments on Earth, providing valuable information about the masses, spins, and other properties of the merging black holes. Another approach is to study the echoes of light from the accretion disks surrounding black holes. These disks, composed of superheated gas and dust spiraling towards the event horizon, emit X-rays that can be distorted and delayed by the black hole's gravity. By analyzing these echoes, scientists can learn about the structure of space-time near the black hole and potentially test the limits of general relativity. Section 1. Gravity's Architects, Shaping Cosmic Structures. Black holes are more than just fascinating objects of scientific curiosity. They are fundamental players in the grand cosmic drama, shaping the universe on the largest scales. Their immense gravity, extending far beyond their event horizons, influences the formation and evolution of galaxies, the building blocks of the cosmos. Imagine the early universe, a chaotic sea of gas and dust expanding outward from the Big Bang. Gravity, the weakest of the fundamental forces yet relentless in its pull, began to draw together these primordial ingredients, forming clumps of matter that grew denser over time. These clumps, destined to become galaxies, were profoundly influenced by the presence of black holes. Black holes, acting as gravitational seeds, accelerated the accumulation of matter within these proto-galaxies. Their immense gravitational pull drew in surrounding gas and dust, providing the raw material for star formation. Thus, black holes played a crucial role in igniting the first stars and shaping the structure of the early universe. Section 2. Galactic Centers, where black holes hold sway. At the heart of most, if not all, large galaxies lies a supermassive black hole, a gravitational anchor around which billions of stars revolve. These behemoths, millions or even billions of times the mass of our Sun, exert a profound influence on the dynamics and evolution of their host galaxies. Imagine a vast city at night, its lights tracing out the intricate network of streets and buildings. Similarly, the stars in a galaxy trace out the gravitational influence of the supermassive black hole at its center. Their orbits, shaped by the black hole's gravity, reveal the presence of this unseen giant. The relationship between a galaxy and its central black hole is a complex interplay of gravity, gas flows, and star formation. The black hole's gravity can drive gas clouds towards the galactic center, fueling periods of intense star formation. These bursts of starbirth can, in turn, influence the growth of the black hole, as some of the newly formed stars end their lives as supernovae, leaving behind black hole remnants. Section 3. Cosmic engines powering the most luminous objects. While black holes themselves are invisible, their presence can be inferred from the energetic phenomena they generate. As matter falls towards a black hole, it forms an accretion disk, a swirling disk of gas and dust heated to millions of degrees by friction and gravitational compression. Imagine water spiraling down a drain, its speed increasing as it gets closer to the center. Similarly, matter in an accretion disk spirals inwards towards the black hole, its temperature rising dramatically as it is compressed and accelerated by the black hole's immense gravity. These accretion disks can outshine entire galaxies, emitting intense radiation across the electromagnetic spectrum, from radio waves to X-rays. Some black holes, known as quasars, are among the most luminous objects in the universe. They're powerful jets of energy, extending for thousands of light years. Section 4. Time travelers, exploring the depths of spacetime. Black holes, with their extreme gravity, offer a unique opportunity to explore time dilation. Imagine two identical clocks, one placed far away from a black hole and the other near its event horizon. The clock near the black hole ticks slower due to stronger gravity. This effect has been verified on Earth using atomic clocks. Section 5. Gravitational wave astronomy. Listening to the symphony of the cosmos. For centuries, astronomers have relied on light in its various forms to study the universe. However, a new window into the cosmos has opened in recent decades: gravitational wave astronomy. This revolutionary field allows us to detect ripples in the fabric of spacetime itself, caused by the acceleration of massive objects, such as black holes and neutron stars. Imagine a pond disturbed by a pebble, sending out ripples that propagate across the surface. Similarly, the acceleration of massive objects creates gravitational waves, ripples in spacetime that travel at the speed of light, carrying information about the objects that created them. The detection of gravitational waves, a feat achieved for the first time in 2015, has ushered in a new era of astronomy. By studying these cosmic ripples, scientists can learn about the properties of black holes, the dynamics of extreme environments, and the nature of gravity itself. Section 6. Black holes and the fate of the universe. A cosmic perspective. Black holes, with their immense gravity and enigmatic nature, raise profound questions about the ultimate fate of the universe. As they continue to grow by consuming matter and merging with each other, will they eventually dominate the cosmos, leading to a future where black holes are the only remaining objects? The answer to this question depends on various factors, including the rate of black hole growth, the expansion of the universe, and the nature of dark energy, the mysterious force driving the accelerated expansion of the cosmos. Some theories suggest that black holes might eventually evaporate through Hawking radiation, albeit over incredibly long timescales. Regardless of their ultimate fate, black holes provide a unique perspective on the grand cosmic cycle of birth, evolution, and death. They are reminders of the immense power of gravity, the limits of our current understanding of physics, and the boundless mysteries that the universe continues to hold. Section 1. A new era of discovery. Unveiling the unseen. For centuries, black holes existed solely as theoretical constructs, predictions of Einstein's theory of general relativity, but hidden from direct observation. However, recent advancements in technology and collaborative efforts among scientists have ushered in a new era of discovery, pushing the boundaries of our understanding of these cosmic enigmas. Imagine trying to study a distant object shrouded in darkness. You might use a flashlight to illuminate it, or listen for any sounds it might make. Similarly, scientists have developed ingenious methods to study black holes, using the tools of modern astronomy to probe their properties and behavior. From the detection of gravitational waves, ripples in space-time itself, to the capture of the first ever image of a black hole shadow, these groundbreaking achievements have transformed our understanding of these once elusive objects, revealing their true nature as powerful engines driving cosmic evolution. One of the most remarkable feats of modern astronomy was the creation of the Event Horizon Telescope, a global network of radio telescopes working in unison to achieve unprecedented resolution, sharp enough to observe the event horizon of a supermassive black hole. This international collaboration pushed the limits of technology and cooperation. In 2019, the Event Horizon Telescope unveiled the first ever image of a black hole's shadow, a ring of light around the event horizon of the supermassive black hole in M87. While black holes continue to captivate our imagination, other theoretical objects, even more exotic and mind-boggling, have emerged from the depths of theoretical physics, wormholes, and white holes. These hypothetical entities, often relegated to the realm of science fiction, challenge our understanding of space, time, and the nature of reality itself. Imagine a shortcut through space and time, a tunnel connecting distant regions of the universe, or even different universes altogether. That's the basic idea behind a wormhole, a hypothetical bridge through space-time predicted by Einstein's equations of general relativity. White holes, on the other hand, can be thought of as the opposite of black holes. While nothing can escape from a black hole once it crosses the event horizon, nothing can enter a white hole. They are hypothetical regions of space-time where matter and energy can only flow outwards, like a cosmic fountain spewing forth from an unknown source. As we delve deeper into the mysteries of black holes, we embark on a journey into the unknown, pushing the boundaries of our understanding of the universe and our place within it. These cosmic enigmas, once shrouded in darkness and speculation, are gradually revealing their secrets, shedding light on the fundamental laws of physics and the evolution of the cosmos. The study of black holes is a testament to the power of human curiosity, our relentless drive to explore the universe and unravel its mysteries. From the theoretical predictions of Einstein to the technological marvels of the Event Horizon Telescope, we have made remarkable strides in understanding these once elusive objects. Yet, with every discovery, new questions arise, driving us to seek even deeper answers, to refine our theories, and to develop even more powerful tools to probe the cosmos. The enduring allure of black holes lies not only in the answers they provide, but also in the profound questions they continue to pose, inspiring future generations of scientists and explorers to unravel the mysteries of the universe. Black holes stand as a testament to the universe's boundless capacity to inspire awe. These cosmic abysses have emerged from the shadows, their existence confirmed by observational evidence. From the first detection of gravitational waves to the awe-inspiring image of a black hole's shadow, our understanding has undergone a revolution. We have peered into the heart of darkness and emerged with a deeper appreciation for the power of gravity. Yet black holes continue to pose profound questions, pushing the boundaries of our knowledge. The quest to understand black holes is a journey without end, a testament to our insatiable curiosity. The cosmic odyssey continues, fueled by our relentless pursuit of knowledge.